Okay, good afternoon. So, firstly, my apologies. I'm still sort of working through the list of projects that I want to offer. So, it will be a few more days before I'm able to finalize that. This Wednesday, the lecture will be given by my postdoc, Balaji Bharat, and that lecture is going to be on life cycle perspective to energy management, in the sense that taking a look at so operational energy is just kind of part of the story. I touched upon that part very briefly, but when you look at energy, there are all sort of, I guess, links between what you're optimizing in terms of energy and other places or other times at which energy get consumed. So if you look a single product like a computer or an EV or whatnot, you have to consider kind of the cradle to grave type of energy perspective, because you could imagine things being designed which are efficient at runtime but come at a huge cost elsewhere, as well as kind of this linkages between separate energy processes, in the sense that I can maybe make my computer more efficient, but perhaps it comes at the cost of something else, maybe the manufacturing process, or maybe the building, or whatever, some other aspects having taking a negative hit also. So anyway, he's going to talk about that, his sort of background and expertise in that. So that's one thing. The other thing is that my office hours will be impacted also this week. So so what I would like to do is the following: if you need to meet me or talk to me, then send me a note and we'll set up a Skype time. And alternatively, if you really need to meet me in person, then I can do it the coming weekend. If you really need to meet me urgently, then after the class today. But basically, I'm not available starting tomorrow through fairly late Friday. So basically the rest of the week. So those were kind of the main things. So I'm going to wrap up this material that we had started, and then we are going to move to from the consumption side of energy to taking a look a little bit on how to model batteries and kind of the source side of energy a little bit also, again in context of computers. So to briefly recap, what we had seen last time around was that we could model processor, display, radio in kind of these simple parametric model, which were motivated by some underlying hardware characteristics. In case of processor, it was dynamic energy, static energy. In case of displays, again, kind of the dependence on color, dependence on frame rate, those kind of things. And in case of radio, these two different kind of things: the energy because of sending the RF signal over a certain distance, so that's the distance dependent term, and the energy consumed by the electronics, and how kind of roughly speaking the range for which a radio is designed for and has an impact. And generally speaking, for short range radios, receiver becomes the relative ratio of receive and transmit energy kind of increases, and in fact can become greater than 1, and that takes you into a territory where certain things which made sense for long range radios no longer make sense. We also I'd also talked about that how multi-hop depending upon the ratio between the distance dependent term and the distance independent term, you may be in a regime where single hop is more efficient or multi-hop is more efficient. One thing which in many cases comes up, which is also what is it that you are trying to optimize when we say we are optimizing for energy in this particular case. And we often face these things in wireless type devices or sensor networks and these kind of things. So just to like motivate the problem a little bit, imagine a network of sensors, battery operated sensors. They're forming a network, they create some sort of a multi-hop network, send the data back and all. And if we begin to talk about if the task was to make this thing energy efficient and all, So first thing would be, okay, maybe I want the longest lifetime before I have to go and replace battery. But that raises the question, what lifetime are we optimizing? Is my network entirely dead when one node dies out of the many that I may have deployed, or is it dead when a certain fraction dies? So all these kind of other issues, that basic terms like lifetime and all, are not as clear cut as one might think. In case you have energy scavenging or energy harvesting like solar cells or other kind of things, then the definition gets even more complicated. So some of those issues play out, but sticking out here, a very simple radio model works. So for transmit, it is some constant plus another constant times distance to some power. So essentially, I have three constants, and the receive one is even simpler. It's just some energy per bit. Now here I'm ignoring the fact that many radios give you control about the speed. So if there was a speed element, then there will probably be a speed dependent term also. Very intuitively, those of you who have done some comm courses, you might have seen it, but very intuitively what happens is that when I transmit at a higher rate, then each symbol is going, or if you look at a period of time, I'm sending more bits in there. That essentially carries, and so there are two implications of that. Firstly, I have to operate the electronics at a higher rate. Whatever algorithm I was doing has to run at a faster rate. But the other part is, to successfully send at a higher rate, you may have to use coding schemes which pack more bits in each symbol, and those algorithms increase in complexity now, so more work has to be done also. So it's not simply more work in the sense of k times, because I'm sending k bits in a given time unit, but also I'm using more complicated algorithms to kind of do it. So there's a larger increase that would happen. So those kind of complicated behaviors creep in. The closing point I made last time was that just like in CPUs, we face this issue that depending upon the parameters, you may be in a regime where you should just operate at the right speed. That's the optimum strategy. Or you may be in the regime where you should operate as fast as possible, finish, shut the thing down. And just like in CPU, in radios, you have the same possibility. I can run the radio at a very fast speed by basically changing the modular coding scheme so that a higher rate you basically are stacking more bits into each symbol that goes over there, but that comes at a cost. And so in many cases, you may be better off ASAP and shut it down. For example, for things where electronics is a more significant part. So that may happen, for example, for short-range radios, because as I mentioned, short-range radios, receivers dominate, and receivers are all electronic. So in that kind of regime, your better strategy may be transmit quickly, shut it down. But that means I need to have radios which can wake up quickly. And wake up presents, just like CPU in radios, has two components to it. One is the hardware takes some time to wake up. There are clocks and power supplies and stuff like that, and they take some time to kind of come back up. And just like in case of CPUs, you had the operating system which needs to reboot and all. Likewise, in case of radios, from a cold start, you may have to become part of the network. So some synchronization with the network may need to happen, so that protocol overhead comes into play. And again, these were things which early generation protocols didn't pay attention to. So like I mentioned last time, first generation Bluetooth, the so-called classical Bluetooth, was not optimized for it. So when it initially pairs, it can take many seconds, tens of seconds to kind of do that pairing. Likewise for Wi-Fi. But then as these things began to come into play, there were protocol enhancements made, and also Bluetooth Low Energy, for example, is optimized for very rapid syncing, or essentially no syncing. They basically use some advertisement packets to kind of send things out, but these are protocols designed so that that part of the overhead is minimized, somewhat akin to optimizations that took place on operating system side to reduce the time for a cold start, kind of a wake up that is happening. So we see that kind of stuff. So this slide is basically showing the kind of things, the bottleneck that a radio can become if its startup time was not optimized. So again, starting around 2006-7 time frame, this thing came into consciousness, and several radio protocols that have emerged since are explicitly optimized for receive side and optimized for rapid wake up. Whereas if you go to cellular thing, they are really catering to long distance stuff, and their focus has been on making long distance transmission efficient, namely focus on the distance dependent term. And the way they do it is by coming up with better and better codes, more efficient codes, because codes basically give you an energy gain out there. So a different mindset sort of occurs when you begin to optimize for energy. Another thing which, if you think about what are the various things that waste energy in communication, what do you think? Well, in a typical communication scenario, so one is the intrinsic energy of just what we have been focused on, how much energy it takes for me to send the packet out, how much energy it takes to receive. What are the other places where energy gets wasted, I guess is the right term? What all can cause wastage?
Interference and multipath.
Okay, so interference and multipath in what manner? So could you be?
You get more. There is more. You get more transmit power. There is some multiple.
Okay, so there's more interference. Okay, so I need to send at a higher power than pure distance would have justified. Okay, so that's one. What else? So can you think of situations where the energy I spent to send a packet is wasted?
The receiver is not ready to receive.
Okay, receiver is not ready. What else?
It's not able to successfully decode the message.
Okay, message is too noisy. Okay, what else? My protocol was stupid enough to schedule more than one transmitter at the same time, for example, right? I mean, then I collide. So that would be another example. So there are all these opportunities, and so as you might imagine, but eliminating these would be another source of opportunity, namely protocols which minimize the chance of collision and which minimize the possibility that the transmitter is sending and the receiver is not ready, or vice versa. Okay, so the latter alludes to some sort of synchronization type issues, and the former alludes to some sort of a coordination mechanism, that is channel access kind of stuff. So those kind of things are other stuff that creep in also. One other thing which often causes a lot of wastage is the following: the role some crucial parameters can play. So for example, take the issue of packet length. So here, or more precisely, frame length. So if you think about communication, what happens is your lower level device has some stuff, something which is called the physical layer frame, which is sending over the communication link. Inside that is encapsulated your data packet. If you look at this physical layer link, at the beginning of it, it has this what's called as preamble. And the idea behind preamble is that using that preamble, the receiver trains its clock and estimates the characteristics of the channel. Usually the preamble is a well-known, well-advertised bit pattern, so that when the receiver gets it, it learns about how the channel is, how the transmitter's clock frequency is related to receiver's clock frequency, and so it does all this adjustment. Then you have the rest. Then you have the real information, and that information would have the medium access or whatever link level frame, as it's called. Think of it like a packet. So it will have some headers giving the destination address, which node it is, and stuff like that. And then there's a payload component, and inside the payload you will have the network layer packet, your IP packet, for example. And then inside the IP packet, again, there would be some similar structure, some other header and all, because all our things are designed as this nested entity. So all this header and all is an overhead. So if my packet sizes are small, percentage-wise, the header is accounting for more, and that's essentially kind of like my static energy, right? I mean, it's basically relative to the true information. This is basically eating away the stuff. So I would like to have larger packets, but the flip side of larger packets is that they increase the chance of loss, and if a loss happens, I have more damage done. So what you see often is that you have a lot of these radios which are for IoT type applications and all, they're really optimized for shorter packet sizes. 32 bytes, 64 bytes, these kind of numbers are typical. Whereas when you're looking at like your Wi-Fi or internet type things, these are 1500 or even bigger jumbo frames and all. So there is this, so we are operating in this regime where we have shorter packets and all, so that has some advantages, but it also has a disadvantage of having a higher overhead, which kind of results as a consequence. Moreover, there are many applications in this embedded IoT kind of space where we send a little bit of data quite frequently. So like think of something like heart rate monitor. Okay, it is sending perhaps a byte or two, the recent heart rate, and it's probably sending it once, maybe at the rate of let's say a hertz or so, right? That's the typical stuff we send out. So I'm sending very tiny amount of data, but I'll have to pack it in with all these header bytes and all. I cannot delay it because a lot of these applications are time sensitive or delay sensitive, so I cannot do that either. So my efficiency goes down. So if you think in terms of energy per bit, the model I had was ignoring all this stuff because that energy per bit was energy per any bit, not energy per truly useful application bit. So, so that overhead somehow also needs to be kind of factored in and honestly accounted for. So by the time you look at the energy per bit number for the true application relevant information bit is going out, it's going to be a lot higher, particularly in this domain of short range radio applications which send little bit of data kind of thing. So we don't have opportunities for packing lots of data. So these issues are things that one has to kind of keep in mind. And these models are that I've described. They're kind of ignoring those issues. So you have to take these models and then apply to your particular setting. So now, if you look at a complete wireless device of some form, a wireless IoT type device, you have these various components, right? You have the CPU, you have kind of the storage part, you have the radio, you have sensors and all. And if you look at now the overall totality of your platform, it can be in many states because many of them come with some pretty sophisticated finer grained control over the different parts. I could shut down the radio, but the microcontroller may be running, I may disable certain sensors, stuff like that. So you can start thinking of this in terms of these different possible states a system may be, and then you can characterize them in terms of power numbers and all. So I have picked some kind of old examples because in early days of the field, people would characterize these things a lot. And you would see that there's a fair bit of diversity, but there are certain numbers which are very important for us. So firstly, certainly how much active stuff matters a lot, but in many applications, I'm mostly asleep. And this goes back to the issue of doing nothing well. And when it comes to that of doing nothing well, in this case, putting things to sleep and waking up, there are two numbers which become important. That how much are we consuming when we are in idle or standby mode, depending upon where you are going. And the other thing is this one, wake up number. And you see a fair bit of diversity emerging there, depending upon whether the designers paid attention. And I kind of offered this one because in these early days, for wake up, you see 6 microseconds versus 180 microseconds, quite significant differences. And so even now, you would see that there are, by the time you look at the combination of processor and operating system and all, you may have vastly distinct thing. And I guess what I'm trying to point out is that if you care about power, if you are in a setting where you're duty cycling, these are numbers you need to look at. These are not the headline numbers. These are not the one which is, oh, it's 1 milliwatt when it is computing. In fact, oftentimes that's a smaller contribution to overall lifetime energy. If I have a system like my heart rate sensor example, it's sending a tiny packet every second, let's say. It probably takes a few milliseconds to measure the heart rate. A packet at typical speeds that Bluetooth and offer is a few milliseconds. So every second, I'm probably running maybe 10 milliseconds, maybe 50 milliseconds. Rest of the time, I can be asleep. I'm doing nothing. So the energy taken during that time is more important than the energy which is consumed while you are actually doing the stuff, because when you look at the lifetime integral, it's going to be that idle time which is going to dominate, and many applications are like that. That is, their inherent they're inherently low duty cycle applications, and for those, worrying about the standby and idle and the wake up time, and likewise the radio wake up, these are more important numbers than what your active mode power consumption or receive and transmit energy might be. So complicated set of things, but you need to kind of analyze these things carefully. Any questions on this? Okay, so the other thing that you have to take into account also is that these numbers are all very uncertain. Okay, and a point I want to bring out is that they are so uncertain that you have to be careful about making mistakes. So there is a problem which the reason they are uncertain is that there is a high degree of variation arising from a few different sources. One is obviously workload differs. So that's a given. That's true for any system. But more importantly, as our devices have been shrinking and kind of nanoscale technologies and stuff like that, we are into a regime where the manufacturing process itself, the way these chips are designed and stuff like that, that has increased the performance variability that the hardware has. So when a data sheet number says this processor consumes 1 watt at 1 gigahertz clock rate, what you should also look at is what's the spread. And you will see that over the years that spread has been going up and up. In fact, the way we have been able to achieve scaling of hardware technology is coming at the cost of that increased spread. So, so let's look at these things. So the term used for this thing is process variation. That is, the manufacturing process itself creates hardware whose power characteristics are variable. And so somehow you need to be, at the very least, be aware of it, but perhaps exploit it. So what this is showing is there are 5 identical, some old Intel Pentium processors running a standard benchmark called LinMac, and there are 10% power variation. Okay, so one of the things that I'm pointing out here is that if you see a paper which says, hey, I have a 5% improvement over my peer and all, well, I mean, it's less than the noise that exists because of variation to begin with. So this is an example of variation which is happening in active mode power due to process variation. I'll show numbers later. Hopefully, I have out here that the leakage mode power, the one which is consumed while the thing is idle, the variation is even more there. One of my former students did his PhD in kind of the space, and a lot of his measurements showed that for ARM processors and all of around 3-4 years ago, you're talking not about 10%, but you're talking about 10x difference in leakage power consumption across nominally identical devices. I mean, there's different chips for the same design made on different wafers at different times. So this and as I talked about that for designs which are low duty cycle, it's the sleep mode power which matters a lot, and if sleep mode power had that amount of variation, you can see significant amount of variation in the system lifetime resulting from that. So something to sort of be cognizant of. Then there are variations from design, and what I refer to out here is that modern systems often depend upon standards. So the system may say you need whatever a memory DIMM for DDR4 standard. So you might think, okay, I'll go ahead and buy a DDR for DIMM, and they're all the same. But they may be designed very differently internally, and therefore there can be a significant power variation across them, across vendors, across parts of parts from kind of different lines of the same vendor. So nominally they are identical in the sense they're functionally identical. They're meeting the same standard. You are supposed to be able to virtually replace them, but you would see that there is a big spread that exists out there. So in this particular case, memory following DDR2 parts identical performance specification, but huge difference in power.
Have they tried to like benchmark different DDR3 because DDR2 because they have the identical performance specification, but doesn't mean they have like truly identical performance, right?
Fair enough. Good point. So, but the thing is, the way these things are sold and the way they are incorporated in the system is that does the part meet a particular specification. So, if you're on the market and your computer needs DDR2 DRAM, you go and buy that. But thing is that there is a reasonable amount of variation in there. You are right that deep down it could be that the manufacturer took the lazy strategy or maybe over-designed the system and all that. All possibilities and probably account for this variation. But from the end user perspective, the variation is there. Okay, and so this is not as if they were being sold as low power DDR or high performance. They're identical performance. They're meeting the same standard requirements, but that variation is there. Then you have variation from environmental conditions. I referred to earlier that temperature affects leakage and active power consumption and all. So all these things kind of impact things, and particularly for things which are deployed out in the open, stuff which is deployed by military, for example, or by environmental scientists and stuff like that. They're often sitting in settings which are not like your computer sitting in an air-conditioned server room. These are systems which are seeing wide variation in temperature levels and all. Your automobile electronics, they all kind of fall into that characteristic. But even in well-controlled settings like data centers and all, it's not as if temperature is perfectly stable. There are fluctuations and all happening depending upon the workload. And what these are, I think, plots from IBM. What basically showing is that look, there is a big interplay that happens out there, and therefore environmental conditions are a factor, and you have to sort of somehow account for that because they vary also. One other point I wanted to make in this realm is that when you are, again from a system designer perspective, when you are looking at your choices of parts that you may use, there's a difference between low power and energy efficient, and which one is better suited depends upon your application, but something that you have to be aware of. And perhaps the best way to characterize this thing is that I may have processors whose power consumption is low, but by the time you look at their clock rate and their architectural capabilities, the time they take to do the same work may be in the opposite direction. So I may have two processors, one is indeed lower power, that is when I'm running it at maximum speed and all, it consumes less power than the other one. But if it consumes 2 times less power but takes 3 times longer time, then it takes more energy. And that is something to be aware of. And what you often see is that there is a tension between these two. So there are processors which are very low power, which consume very low energy per instruction. So I've listed some out here. These are like the real low end, ultra low power microcontroller type stuff. So they often tend to be in a fraction of a nanojoule per instruction. But that doesn't mean that they are necessarily better, because if I look at, for example, a bigger processor, it may be in few nanojoules or maybe tens of nanojoules per instruction. But the bigger processor is probably likely has wider word width, likely has a more sophisticated architecture, perhaps more cache, stuff like that. And the net effect of that may be that the same task it does at a much shorter time. So now the thing that you face really is that in some applications, indeed, this may be sufficient, and you may also be peak power limited, namely you care about how much dissipation is happening. I refer to applications like implantables and all. But then if battery life is an issue, then the energy consumed becomes important, and sometimes you're actually more often than not, the choices are such that bigger, more sophisticated things tend to be more efficient from an energy perspective, particularly when they're doing bulk work, whereas simpler things tend to be lower power and would be better off when they are doing little small tasks. Or so this little versus big difference, simple versus complex difference plays out. Simple things have lower static power just because they are simpler. They can more rapidly wake up, change state. But if you throw at them a big task, then they will take more energy. So, for example, my ARM A15 versus an ARM A0. ARM A0 would be very good if my task was measure that heart rate every second. On the other hand, A15 would be better off if I'm looking at the energy consumed to, let's say, do an FFT over a collection of subsamples. So they may just shine in different settings. And again, so just don't go by the power number because it hides a lot of nuances behind it. So energy efficiency then has these different facets, or energy perspective, these different facets. So you can talk about what is the efficiency in the active mode when you're actually doing something, and there you have knobs still. So in case of processor, you can change voltage frequency. In case of radio, you can change modulation speed, the data rate, and the transmit power. In case of sensors, you can change things like sample rate, number of bits, each sample and all. Then you have sleep mode efficiency, and this is that I was referring to, like how much power it consumes when you put it into sleep mode of some form. Okay, usually processors provide this capability that you can put them into the sleep mode, and then in response to some sort of interrupt or a timer interrupt, they can come out of the sleep mode. Radios provide similar things, like you can network interfaces, you can put them into sleep mode, and then a packet of some special type can wake them up, or a timer can wake them up. So sleep mode is the second number, and the final thing is the transition cost. How much does it cost to go from sleep to active, and how much it costs from active to sleep? In case of active to sleep, you have to save state, and in case of sleep to active, you have to restore state. So that takes time. That in itself can have both time cost and energy cost. So this is basically showing kind of some extreme case of like a simple processor and a complicated processor, and doing some certain computation, FFT, cyclic redundancy check, and a FIR filter. And what you see out here is that a big processor, which is a shorter curves, are orders of magnitude 10x or so or more efficient, because these are computationally complicated tasks. On the other hand, the big processor takes a hit because its transition times and all are larger due to a combination of more complicated hardware and the more complicated, more complex, more state in the software side of things. So this is in a way kind of a bit of a bad story, because what I'm also now saying is that you cannot design, or that our technology choices tend to be that they either shine for the sleep thing or they shine for bulk computation. You tend not to have both attributes simultaneously in the same hardware, because these are essentially a function of complexity, of the architectural complexity. So faced with this kind of situation where I have two extreme choices, this is something you face in system design, system architecture often. A great example is memories. We have fast but small SRAMs. We have bigger but slower DRAMs. We have even bigger and even slower disks, and we combine them in a hierarchy. So we shift work between them. It's the same thing here. You can imagine multiple processors, multiple radios, multiple sensors, and you activate, deactivate them. So this is kind of a solution to the energy proportionality issue, which is if I want to design a system which looks energy proportional, then one of the ways I can do is to take heterogeneous things which reside at different points and stitch them together to mimic or approximate an energy proportional thing. So that would be kind of the idea out here. This fact that we have this tension between active mode and sleep mode is something that uh, uh, at least I kind of consider it all, like I said, fundamental, because it's something to do with complexity. But even if you don't believe that, the realistic technology choices are like that. You basically would see this tension play out. That radios which are very good in energy per bit end up taking a hit in sleep mode power and vice versa, particularly when you have a lot of work to do and all. So active mode energy efficiency versus the ability to do power management, these are often at odds. So this was at radio, this is for speed. Generally speaking, so what I've shown out here is, this is like a little thing, simple radio, simple processor, and this is a complex thing, big radio, biggish processor and all. And you would see things like a lot of these numbers and all basically means that energy and energy per computation and energy per bit, they kind of are in favor of the big guy. Okay, that is, they go up. Energy per watt goes up. Okay, whereas sleep stuff favors the little guy. So it goes up as you come down. And this is something you'll see just generally in the system. So you can within a system you can combine parts of different types, or at the network level you can have network nodes of different types. You can have energy rich nodes which are responsible for bulk stuff, and you can have tinier nodes which are more duty cycle and are excel at that, and sort of then your overall network or whatever overall network system is energy proportional like that. Yeah. So that was a bit of the consumption story. Let me ask you one thing. So in case of processors, it's obviously the act of wake up is relatively easy. It's a local wake up. The user presses a button or something like that. If I put a radio to sleep, what kind of strategies can you think of waking it up? See, the problem with radio is that if the receiver puts this radio to sleep, then how can the sender wake it up? So
maybe we can lower the throughput of the receiver and
say it again?
Lower the sampling rate or throughput of the receiver, and probably at a certain time we just give it a long time beat and to wake the receiver up and to turn.
Okay, so I can, but somehow the receiver has to kind of wake up. There's no other strategy that you can that one would imagine, in the sense that if I have to get the wake up signal, I have to listen, but I'm supposed to be sleeping. So really, kind of the only way around it is that I periodically wake up and check. Either that, or I designate. Okay.
You have a separate wake up receiver.
You have a separate wake up receiver. And I go to sleep and I tell my daughter to wake me up when something important comes up, right? I mean, that kind of thing. So you design some wake up radio and task it for doing that. And that strategy is very commonly used. There are lots of names for it. It's something called order wire radio. That's what military calls it. But kind of the basic idea is there's a secondary radio whose sole purpose is to listen for this, hey, wake up kind of thing. And then you activate the main system. So you can actually, there are companies who sell these kind of wake-up radios in bigger systems. In 80s and 90s, I often used to see that people would use pagers in that role. So you might recall there was such thing as pagers. They are no longer there, but these are basically they were designed to be very power efficient. The battery would last for weeks, unlike your cell phones and all, and they would work from separate paging network. So what I'd seen a lot of systems where they would take a pager and hook it up to the main radio receiver, and so you would send a page and then it would activate the main radio receiver because the pagers were just so efficient energy wise. The same kind of concept is there. So long story short, you can either have your regular radio wake up, listen, is there someone, go back. In that case, it's kind of a You're not truly putting it to sleep, you're kind of doing a polling. Or you can have two radios, put the main radio to sleep, and then have this energy efficient radio purely designed for this wake up thing. And since it's just doing that, it can be simpler, it can do some more optimization just for that. And there are companies now which sell products these are very simple radio chips designed for this kind of a wake up application.
To sort of extend the first idea, we have a sort of a buffering scheme for the sender requests, and once suppose our queue is full, then some sort of control logic wakes up and sleeping.
Well, remember that for something to reach the buffer, the radio receiver has to be on, right? I mean, so unlike your CPU where a key or a sensor signal will wake up and all, here the only way the radio can receive something is by actually listening to a packet. So what is done is sometimes there is a hybrid thing that you may have the main radio receiver chain, but somewhere along that pathway, a little part right next to the antenna may be kept on. It may simply do some simple energy detection, not a full-blown decoding of the packet and all, or it might be a very simple decoder, okay, and then it wakes up rest of the chain. So those kind of ideas are there. You can also design radios to scale. There are radios like maybe they will just listen in one tiny sub-band as opposed to kind of the whole wider spectrum and all. So there are different ways to do it, but point is a true notion of sleeping is not possible with radios. Something has to be up, either some part of your current radio or a second radio, okay? The only true sleep could be something which is time-based, which is we agree that next time we will talk is at 10 p.m. and we both go to sleep. And as long as we have some way of precisely knowing it is 10 p.m., we are okay. And in fact, motivated by this and the fact that there is a class of application which military tends to be particularly interested in, where you do see this kind of operational paradigm, there was a lot of effort that DARPA had put to create chip-scale atomic clocks which can maintain time for long durations. So you can agree a priori, you'll wake up at 5 p.m. and same thing, and you wake up and you squirt the bits out and go back to sleep. No synchronization needed, nothing, none of that stuff about are you up now, can we exchange messages. You just rely on a very, very precise clock. So the whole technology of chip-scale atomic clocks was basically driven by this application. And some of the scenarios and all which call for proposals had asked for are things like sensors which go deep under the Arctic Ocean, and 20 years later they are supposed to receive a signal and wake up simultaneously and exchange messages. Okay, so you're talking about like really, I mean, you can imagine the kind of applications obviously these things are meant for. Point is, long dormant systems and then suddenly waking up very rapidly. Okay, and that stresses this wake up thing. Okay, so next thing that I want to move towards is, so we have looked at the consumption side, and hopefully, at least for some of the things we have first order models. These models are by no means perfect or rich enough, but they give you a starting point. And again, the main takeaway that I'll leave is that there are lots of knobs, regimes, dependence upon speed, power, stuff like that. And the other thing is that a lot of these first order models do actually pretty good. So now I want to flip gears and really look at the other side, which is also important. Where does the energy come from, and what role would that have to play? And most of the focus I'll have is on batteries, because that is where battery operated devices are where things really get dicey. So when you think about batteries, they kind of really play a couple of different roles. One role that batteries play is that they are the source of electrical energy for untethered systems. So I basically buy a battery and put it in, and that's like the fuel which is supplied. And the other one is that batteries can also, rechargeable batteries can also act as storage, which can help you cope with intermittency, namely If your sensor is driven by solar energy or stuff like that, then there will be outages. So instead of, so you basically use battery to kind of smooth things over. It's kind of a low pass filter which helps smooth the energy supply. And at one level, you can argue that artificially making a distinction between the two, and one way of looking at any battery is that it is helping cope with intermittency in the sense when we replace the battery or when I plug it in and on. But I still think that these two cases deserve to be treated separately. So, irrespective, under the hood, batteries are basically made of what are called as cells, which are essentially little packages of some electrochemical material with a couple of terminals, anode, cathode, going back to your old chemistry. But the main thing is, at the end of the day, some chemical voltage difference and all gives rise to a potential, and which is the energy that we draw upon doing it. For our purposes, one of the things that matters is that batteries come in two varieties, primary and secondary. Primaries are disposable batteries, and secondary are the ones where we can reverse the process and recharge them also. What matters for us is, as a system designer, is that battery would have certain characteristics which matter to us in terms of how much energy per unit volume, how much energy per unit mass, how much power can it supply, what is its voltage, how long will it last, what is the leakage rate, as in I charge the battery and every delta time it is losing some of it. All these are numbers and they are dependent upon the chemistry of the battery. There are a bunch of other things. How many times can I recharge them, and also all these things kind of play out in the overall picture. Some of them affect the physical form factor, and others affect the way we run these systems. A lot of variations in across different battery chemistries that happen in this regard. I'm going to skip a few slides here. Suffice it to say that the most cutting edge technology that you would largely find are the lithium based batteries. There are a bunch of different lithium chemistries. You'll see lithium poly, lithium ion, these kind of things, but by and large, they are lithium based batteries. But having said that, there are a bunch of other stuff, and in some applications, other stuff do matter. Like, for example, applications where you have to supply a rush of current, okay, you might go for a different chemistry. Or applications where you may need to operate in high temperature or harsh conditions like that. Those often go for other chemistries as well. So there are a whole bunch of these battery chemistries out there. Okay, some of them you may have lithium ion already, NiCad, nickel metal hydride, some less so. Fair bit of variation in how much energy they can store per volume here, per mass, per unit mass out there, and the cost structures that they lead to. So fair bit of diversity that exists. In some cases, other aspects of the battery besides how much energy they store come into play, like for example what voltage they are able to supply, because your circuit needs certain voltage. So if the battery voltage is too low, you will need two of them in series to supply you the voltage, and that may have implications in size. So all those kind of factors help drive choices of the battery. So what's been happening is a couple of things. So firstly, there is in many cases becoming feasible that maybe you can replace batteries by capacitors which are capable of storing high amount of energy. So capacitors' disadvantage is they are not as dense as batteries. Capacitors' advantage is we can charge them very rapidly and all. And so a lot of work is happening, particularly with newer materials and all, that capacitors are emerging as the competition. And the other is making batteries more more system friendly. And one of the things which has happened in recent years is the so-called thin film batteries. You may have heard this term, but basically what thin film batteries do is they take your regular silicon chip and they make a battery in there. Okay, so essentially you can really have battery integrated along with electronics inside the same package, basically there. So very tiny stuff. So there's a cross section out there, but essentially battery on chip, and these are really very tiny stuff. So miniaturization in that regard, which is happening. So let's see. Yeah, I'm going to skip that for now. There are other things like nuclear microbatteries. These are used in applications like, yeah, go ahead.
What are the current barriers to adoption for thin film batteries other than cost?
How much size? Like, I mean, in the sense that if you are a Samsung trying to put a large battery for your Note 7 to burn, a lot of thin film batteries will not be a good choice. Well, I'm kidding, but point is that if you have a lot of volume, then it's better to create. You don't gain any advantage from thin film. Okay, so the thin film shines when you are putting a tiny amount of battery in a space limited kind of a setting. Okay, so and thin film is obviously, as I said, cost. Okay.
So that would be kind of nice for something like an oscillator or a clock.
Implants, wearables, these kind of things. Yeah. So I mean, we have used it. These are somewhat more boutique. I mean, you don't buy them from Spark Fun and all kind of stuff. I mean, these are inherently more require more involvement at the circuit design phase because they kind of get soldered onto your board like a chip and all. So it has different applications there. Okay. And actually, what I was showing out here, and we'll touch upon this thing later, is the following: that you see these kind of plots, which basically what they show is that when we talk about the capacity of a battery, so in previous tables I just had these numbers, so many joules per unit mass or so many joules per unit volume. The story behind it is more complicated, and we'll see how it affects the system, it affects kind of the upper layers of the system. But this is showing is the following: that at a particular temperature, this left plot, for different amount of current, that's the 0.02 to 10 milliamp per centimeter square, I achieve different amount of capacity. So what's happening out here is I start the battery fully charged, and then as I discharge it, the voltage falls, and at some stage the voltage reaches some sort of a cutoff voltage, which we consider to be the battery be no longer sufficient. And what you see is that the rate at which we discharge the battery affects this characteristic, the net energy I'm able to get out of it. Or another way of saying the following: I take a battery with a certain amount of energy, and if I discharge it with a high current, I will extract fewer joules out of it than if I were to draw a tiny amount of current. Then I can draw more out of the battery. So battery is not simply a bucket of energy, but it's a bucket of energy whose capacity is a function of the rate at which I'm drawing from it. So these plots are kind of showing that part, and we'll visit this thing a little bit later. Nuclear microbatteries. So this is again another boutique end, which is systems which need to last really long time. So these are used in like emergency lights. They're used in actually they have been used in satellites, underwater systems, implants, this sort of stuff. So that's another one, more boutique. There are lot of effort. So this slide is a couple of years old. So the latest update on this front is the largest batteries and how rapidly you can charge and all. So there's an interesting experiment going on now with 3 very large lithium-ion installations being done in California as grid-scale batteries. One which Tesla is doing up here in Simi Valley, and a couple which a company called AES is doing down, one in San Diego and one in some other city, again, south of here. And what's happening is these are kind of mentioned earlier that one of the challenge with renewables like wind and solar and all is that they fluctuate over time. And one of the ways we can address that is by having energy storage acting as a buffer at the grid scale. But to create that large scale buffer cost efficiently is a challenge. But I guess the utilities in California are kind of doing this experiment, so to say. It's a pretty large scale things. These are batteries like the one in San Diego can apparently essentially supply the energy needed for a small city for the whole day. Okay, so you're talking about really massive scale. What I was reading was that the installation in San Diego is 64 tractor trailers packed with lithium-ion batteries, and that's the cluster. So it's pretty massive going on. So these are so a lot of fun stuff happening in battery. What is interesting for us, and that's why the part I really want to focus on it. How can I model the battery? What does it mean for my system? What parts do I need to worry about it? And the main thing is that you can think of a battery as a pack of energy, and I can just extract those joules out of it. But the story is more subtle because, as I showed with those plots a little bit back, the rate at which I draw the energy affects how much energy I can draw from it. And some of these non-idealities you probably have seen even in the practical, in your own daily life, like your flashlight, if you still have one, might die. Apparently the battery runs out, but then you don't use it for a bit, and then you start turn it on again, and it works. Okay, so there is a relaxation that happens in the battery. So battery wasn't really dead, but it seemed dead. And the other thing which is less noticeable is that if there is a significant mismatch between the load and the battery, then the battery can die very rapidly. If I draw current out of it at a larger rate, then it doesn't live us the expectation that we had. So I can draw less if I draw it a larger rate. So there is a theoretical model, first order model, which would be that a battery is a bucket of energy, and every time I draw certain power, I integrate over time. So what this would suggest is that if I'm trying to design a system, and if I have modeled my processor, my rest of my system, its power states, and if I know what power state it was in, then I essentially have to do an integration of current over with time, and every time I change the state, my current number changes, and at some point, I would say the system would die because I have my integral IT dt added up to the energy which the battery had. But unfortunately, that doesn't work because the energy term in the battery depends upon what I of t was. Okay, so energy is not the bucket of energy. But this is the first order model. Doesn't work very well. So that some years ago, 15 years ago, early days of mobile computing, kind of led to search for better abstractions for this thing. So it's just like saying a processor is not simply something which consumes a constant amount of power. Likewise, battery is not something which you can think of as a constant amount of energy. So in reality, therefore, the capacity of a battery, how much it actually delivers, depends upon the current or the power equivalently, as well as how you what profile. So like for example, if I draw power at a sustained rate versus if I were to duty cycle it, it has an impact on it, as well as what the current health or state of the battery was. So the way battery capacity is measured is that we basically when you buy a battery and say it is whatever 1500 milliwatt hour, what it's really saying is that there is a rated current, which would be in the data sheet. If I were to draw that amount of current from the battery, then it will last that long. Okay. If you were to draw twice the current, it doesn't mean it will last half the time. It will probably last less than half the time. Okay, and so on. So there's a non-linear dependence on that. So capacity printed on a battery is usually the product of 20 hours multiplied by a constant current that the battery can supply for 20 hours at 68 degree Fahrenheit, degree Celsius, at a specified voltage. So to cut through the language, a battery rated at 100 amp hour will deliver 5 amp over a 20-hour period at room temperature. Okay, so that's what it is rated as. So the rated current rating is 5 amps. So essentially, you take this number, divide it by 20 hours. That's the current which was being used for defining it. So if you use a different current, then the product will not remain the same. Okay, because this not will change. So if discharged at 50 amp, it will actually have a lower capacity. And if you discharge it at 1 amp, it will have a higher capacity. But the way these curves look is they kind of flat and then they fall. So you would see these kind of curves which come in a real data sheet where for the rated current there will be some capacity and then kind of curve goes like that. So this is one non-ideality that somehow we need to kind of model. Dependence upon the current. But things are a little bit more complicated. So this is the part which I was mentioning earlier, that you take your flashlight, it dies, and then you wait and it comes back up again. What this is showing is, the strike plot is showing is that if I were to continuously discharge, and if I were to observe the battery state, voltage let's say, then we'll see some sort of smooth degradation and it will die. But if on the other hand, I punctuate the use of battery, that is, I operate it for a while, and then this jump means I stop using it. When for some time I stopped using it, then its voltage jumped up. So it kind of revived, by putting the battery to, by not using the battery, I'm letting the battery relax. And so it basically is rejuvenated and can supply energy to us again. So, these are the two kind of non-idealities that exist in the battery. So the first, yeah, go ahead.
Does this mean that if you recycle, you should expect to see more, not only because you're using less current, but because you're switching batteries?
So the story is not all battery chemistries are equally manifest this effect to the equal extent. So for example, you would see this thing a lot in NiCad or nickel metal hydride. You won't see it to the same extent in lithium ion thing. Okay, so that's one. It also depends upon what the current was to begin with relative to battery's capacity. So this effect will be more dominant if your current was in the range of the battery's rated capacity as opposed to being a very tiny amount of current. So in other words, that duty cycling a tiny amount of current is not going to help out that much. A question I've often offered in homework previously in this course is that let's imagine you had two choices. Remember, we saw these two effects, right? There's a dependence on the current and a dependence. Okay, so let's say you're designing a system, device of some form, which is operating with a certain current. Okay, what is better? Am I better off having? So let's say I give you a bunch of batteries, and you can think of two designs. One design is I put these batteries together in parallel, in effect creating a larger battery, and I draw current from this larger battery. And the other design is that I create a switch. For a little while I use battery 1, then I switch to battery 2, then to battery 3, 4, 5, and come back and do the same thing. Okay, so I switch among them. So the difference is in one case, I'm using all the batteries simultaneously, and I'm drawing one nth my power from each one. In the other case, one nth of the time I'm drawing the peak power from each battery. Okay, and the question is which one is better off? So I'll not say anything more than anybody can see these kind of trade-offs can arise in that setting. So how you use the battery. In fact, this thing takes particularly serious dimension in electric vehicles and all, and for like the EV designers and all, because it's essentially a big, mass of lithium-ion pack. Its management is really the key intellectual property that they have. The rest of the stuff is just motors and metal and all slapped onto it. I mean, what the magic behind EVs really is how they manage the battery pack. Okay, in part in those products, obviously the battery pack is also representing a significant share of the cost of the vehicle also. So it's not like other devices. So there are a lot of these kind of tricky issues and all which come up. The other thing also that happens is that the state of the battery. So batteries also age, just like electronics age, just like mechanics age, batteries age. So So batteries leak, batteries age. So those effects also need to be accounted for. So in these more complicated things like the car or these grid scale energy installations, they actually put all sort of sensors inside the battery to have essentially a state estimate of what is happening inside the battery, so that then you can intelligently pick and choose this thing. So there's a lot that goes on, but that was a long-winded answer to your question. Yeah, a deliberate duty cycle use of the battery is part of your arsenal. The other trade-off that you would see is that now think about so focus on this issue of battery capacity versus discharge current. Am I better off from overall work done before the battery dies perspective? Am I better off running my processor at a lower frequency, lower voltage, and then but drawing current over a longer time because my processor is slower, so I'm going to be, or so will I be able to do more work with this before the battery dies? Because remember now I'm drawing current at a lower rate, drawing current at a lower amount of current, and therefore I will get more out of the battery potentially, right? Because of that discharge current dependence. Or am I better off running the processor more rapidly? And okay, so there is a dependence. How you set your load related to battery, that becomes that matters as well. So on this issue of battery capacity versus discharge current, intuitively what is happening inside is the following. When a battery supplies current, essentially what's happening is the ions inside the electrolyte in the battery, they're moving. And that's a physical process governed by laws of diffusion. So there is a depending upon the diffusion constant, there's a rapidity with which this process can take place. So when I draw a large amount of current, the charges have to more charges have to flow. Okay, so I'm putting more demand on that diffusion process, and it cannot keep up with it. So what happens is that inside the charges are moving to the terminal sluggishly, but I'm consuming them very rapidly. So the queue of charges near the terminal becomes empty, to kind of use that analogy. So even though there is material there inside the battery, but I just suck them out so rapidly that there is a paucity of it near the terminal. So the battery dies quickly. And that also explains the relaxation process. Now I stop doing it, and that electrolyte inside the battery kind of evens out, and it builds up again near the terminal. So the queue near the terminal again replenishes, and now I can again draw material from it. So that's kind of under the hood physical process that explains both these things. So at high currents, the diffusion process cannot keep up. So whereas at low current that doesn't happen. But low current isn't necessarily good either. Okay, so let's take the argument to extreme thing. Let's say so we're saying low current is better. So let's say I don't care about any deadline or anything. So why not just draw current really, really very slowly and do the computation really, really very slowly? Well, the problem is batteries also discharge. So that complicates life, right? I mean, if you use the battery over a longer time, you're taking a hit on that side. This is akin to the static power consumption. There is a static power dissipation from the battery. So that balance needs to be also thought of as well. So just slowing down things to the extreme is not necessarily the answer either. So depending upon the specific system and all, one has to sort of account for these things. What does matter though is that we cannot get away with this simplistic view of the battery as a certain number of joules. Okay, one has to capture some of these non-linearities also. So in the people who do batteries, this thing has been known for a while. So a very common so there are a variety of models that exist for batteries. So the first generation models were simple parametric empirical ones, or they were ones which essentially did a full-blown coupled partial differential equation simulation of the electrochemical system. They were done by electrochemists. Until sometime in 90s and all, when computer scientists began to sort of pay attention to it, because they needed simpler but yet better models which could be used to characterize and manage mobile devices. So then some of the more computationally friendly models began to emerge and all, and I'll go over one of those. And then again, in recent years, because of EVs and all, there's another sort of battery modeling and battery management and all. There's again a lot of attention there. So going back to those first generation models, one very common model is that to model that charge capacity of a battery as C equal to Cp over I to the power alpha. Cp is a constant. So normally our battery model is capacity of the battery is some constant. But here there is a I over alpha term, which is basically saying that as current goes up, then the battery capacity goes down. Okay, so Cp is dependent upon the battery chemistry. Alpha is 0 for an ideal battery. So in an ideal battery, capacity is equal to Cp. But in reality, you'll find that alpha is some positive value. And so that is modeling this current dependent effect. And it's a good first order model. It's better than the constant one, but it does not capture your relaxation kind of effects and all, and it doesn't model the discharge effect that accurately, but it's a very common model which you would see. It's called Puchert formula. And there are many other variants of it, but that's what's called.
In any case, we have negative alpha.
No. Or, I mean, what I've seen is that alpha typically has a value somewhere in the vicinity of 1. Okay. There are many different ways this thing is presented. So this is one of the ways you would see Puchert formula. Yeah.
So when you say beta equals 1 plus alpha, is alpha the Puchert's constant or is it beta?
I have not gone into beta yet, so
Oh.
I'm only talking about the top part here.
Oh.
Okay. Yeah. So let's do some reformulation of this. Assume current is in amperes and capacity is in ampere hour. Then Cp is the capacity in ampere hour. Then my current was 1 amp. So that's how Cp is defined. Let's say L is the lifetime of the battery. If I were to draw current from the battery at I amp. Okay. One thing to bear in mind is batteries provide a fixed voltage. So essentially power and current are interchangeable because the voltage we assume to be fixed for the duration. Okay. Modeling voltage is much harder, and therefore all these models just assume that voltage remains constant, and then when the battery dies, voltage just plummets. Okay. In reality, voltage degrades, and therefore for the same power you need more current drawn from the battery. Going back out here, so L is going to be equal to C over I, and then you do some plugging in, so you end up with this thing, that capacity of the battery, Cp, or Cp, not capacity, Cp is equal to L times I to the power 1 plus alpha. Wikipedia has a slightly different definition. So beta, which is that 1 plus alpha, is the Puchert constant, and beta is 1 for the ideal battery. This one is the other way that things are presented, and the alpha equal to 0 is for the ideal battery, but alpha is not what is called the Puchert's constant, to answer your question. So Puchert's law has
Sorry, one more question. Is the I there, is that nominal or is that the
I is the actual current, and it is in amps. So unfortunately, the way this formula is defined is there is an implied specific unit associated with these things, because Cp is defined as the number of amp hours when the current was 1 amp. Okay, so that's how Cp is defined, and then everything else kind of follows from that.
So if we want to use a non-discharge current of 1 amp, we have to use a different formula.
If you want to, so I is the actual current you are using in amp.
Is that for charging or discharging?
There's no discharging. There's no charging model.
Okay.
Okay, this is discharging.
Okay.
Okay. Yeah. a few years ago in this course, I had a project where which didn't work out that well, but we were trying to develop a charging model for this thing. Okay, but turns out to be trickier to model. We were just doing data fitting kind of stuff. Okay, I haven't tracked the literature in the past couple of years in that domain, so there might be something. I'm sure companies like Tesla and all probably absolutely would have done this thing, but in the more mobile computer science type literature, I haven't seen. So these kind of non-abilities are very important to capture in EVs kind of stuff, and certainly those grid scale things and all. So part of the thing also is that in vehicles and all, your driving habits and all play an important role. So right, I mean, so for example, if you look at an EV, they would say this is the range, but then if you make use of Tesla's whatever ludicrous plus acceleration mode, for the same mile driven, you're actually going to drain a lot of the battery, right? I mean, so because you're drawing things at a higher current. So that aspect has to be taken into account, and that is where you would see that these vehicles offer you the rated range and the range which depends upon your driving habit, and then they give an estimate there. One project idea that I'm trying that I think would be interesting to pursue is that as these vehicles also have autonomous driving mode, so you could imagine that as you do navigation and all, you could pick a route which would be most battery range friendly. And let me bring that point out also. These vehicles implicitly also benefit from gravity or are hurt by gravity. So in the sense when you're going downhill versus uphill. So there's one website which I've seen where you plug in your address and it asks for how many people you are going to carry and stuff like that and all. And it basically charts a route for you which takes you through electric chargers so that you will be safe in the sense that you will have adequate charging opportunity. And what it does is it takes into account the benefit of this kind of stuff, this kind of thing. So just generally, so in that case, it is doing it. The project idea I have is the following: that if I have to go from point A to B, could you find me the most energy efficient route? Modeling these kind of things and also kind of doing a simple first order model out there, and perhaps even see how that particular website is doing it and all, and kind of investigate this part. Last 202A, there was a project which was about fuel, and I think there was the student who did it was here now using. So the project there was to in the navigation app, kind of make sure that you would be near fuel stations and all. Okay, so that was for a gasoline car. I think EVs offer a very interesting blend of possibilities out there. Another interesting project related to this thing also is that the EVs being used as storage for the grid. So I put my car in a parking lot. I'm going to come back in the evening. I need my car charged by then, but in the middle, the car could be used as a transient storage mechanism, and kind of looking at its impact. So there are various ideas at this intersection of batteries, EVs, and kind of the broader grid that one could do. Okay, so switching back out here, there are alternative representations of Euclid's law which are done. So I've sort of shown one out here. So one thing that I want to point out is the following: is the CP. Like given a battery, how are you going to kind of find these parameters and all of that? So unfortunately, it's not something that is given. So what we may have is usually we do not have the capacity at that 1 ampere discharge. That's not given to you. So say instead we are given the battery's capacity at some rated current in ampere hour. That's what batteries score. Remember I described earlier that when batteries say that their capacity is so many amp hour, then the current at which that battery is rated is that number divided by 20 hours. Essentially, the battery capacity is defined for that current, which will lead to a 20-hour battery lifetime. So that's the number you usually have from the data sheet of the battery. Well, you don't have a number at 1 amp. So somehow you need to kind of convert this stuff. So you are so some sort of algebra and all kind of leads you to that. That's you can come up with the C value that you actually need in terms of those rated numbers that you have. So you will have an actual. So instead of so you're not given that CP and all. You're basically given that there is a lifetime of 20 hours at a rated capacity of so many amp hour, so many amp hour. And what you need is that you are plugging in. You have an actual draw. Your system is designed to draw a certain amount of current, and then what you want to know is what is the actual capacity that I'm going to get, and from that you can also get the actual lifetime. So these are all simple algebra manipulations, but point I want to make is that there are ways that you can derive this stuff. Another thing that batteries that you would also see is that they often give you these other kind of plots. So besides the discharge one, there is something called Ragone plot, which is often shown, which gives you energy density versus power density. And this matters a lot also. Very broadly, there are applications which are power intensive. That is, they don't need to do a whole lot of work and all, but when they do, they have a very high power demand. A great example, obviously, something like a camera flash. But there are a lot of other cases also where there's a transient demand which is very large. Disks starting to spin up. Battery in a drone, when the drone is taking off, the initial stuff can require a large amount of current. On the other hand, there are applications where energy density is what you care about. Ideally, of course, I would like a battery which is in the far right corner, high in power density and high in current density. But conventional batteries are very great at energy density. They can store a lot of energy, but they are not that great in power density. They cannot supply a whole lot of current. Capacitors excel in another dimension. Capacitors are very good at supplying that burst of energy, but they don't store a whole lot of energy, orders of magnitude lower. But they are shifting up. So these so-called ultra capacitors, fine, they are larger capacitors in the sense they have bigger capacitors for the same volume, and therefore they can store more stuff. There is some pretty cool stuff happening here at UCLA in the chemistry and material science department with graphene sheets and using those to create really very high capacity capacitors. So kind of the hope is that at some point capacitors become in this regime and now they basically replace batteries. Capacitors do have some other disadvantages. So capacitors can supply a lot of power. In the reverse also, they can suck a lot of power very rapidly. So you can charge them very rapidly. So there have been some efforts on putting a capacitor along with a battery in your phone so that I can charge it rapidly and the capacitor, so you get an initial sort of sufficient charge and while your battery then charges up. A capacitor disadvantage is it leaks more. Okay, so unless you do some stuff, okay, and also capacitors also age. So there are sort of cons also. But this plot was an attempt to show that. So going back to our Fuker's formula and the kind of implications it might have, let's go to that example that I was mentioning that I care about. I'm designing a system and I want to match my processor operation with the battery so that I get the most work done. That's my goal. Okay. So perhaps it is something where just the bulk amount of work done is what I care about. You can reformulate the problem in that direction. So total work is speed times lifetime. So if I make some change to the system, and by change I mean like for example I operate it at a different voltage frequency setting or things like that, Then let's say I made a change to a system so that its performance increased by a factor of n and its power increased by a factor of x. So since the performance increased by a factor of n, the the speed will go up, but since power increased by factor of x, so the capacity that I can see will go down, Euclid's formula. And so when I take the product of the work I would be able to do, it would be the product of those things. So it looks like n times x to the power minus 1 plus alpha. So point out being that there is kind of a more complicated relationship. So let's say I reduce the clock frequency by a factor of n. It reduces power by a factor of n. And it reduces speed by a factor of n. I plug that into formula, work done changes by n to the power alpha. This is entirely because of the non-ideality of the battery. If the battery was ideal, alpha would have been 0, and as expected, the work done would have remained the same. But because of this non-ideality, as I reduce the clock frequency, I am actually seeing this effect that the work done is changing, not by factor of 1, not remaining constant, but there's a change that is happening. In this particular case, I'm increasing the work done, n to the power alpha, so alpha being whatever, somewhere close to 1, so it's kind of increasing actually. However, I cannot keep reducing the frequency because other effects come into play. In the extreme, when I go very low, the leakage energy of the system will begin to dominate. And the other thing is also battery leakage will become a factor also. So you cannot just keep running slower and slower and slower. So there would be, if you take those static stuff into account, there would be some sort of an optimum frequency that you should operate the system at, which rightly balances what the processor is doing and what the battery is doing. So there are non-idealities on both sides. There is the role of static energy, static power on the processor side, and there's the role of static leakage, and this non-ideality on the battery side. Additionally, the complication comes as system performance does not change linearly with frequency. So what I mean by that is, as I change the speed of the processor, its impact on the performance in terms of speed is not simply by a factor of n, because caches and all those kind of things are complicate that part. And also not everything in the system changes when I change the clock frequency, because the systems depend upon I/O interfaces, and I/O interfaces operate at some rate which is independent of the system clock frequency. So all those things complicate life further, but the central message that I want to take away is that there's going to be some sweet spot, or perhaps yet another way of saying is that your battery should be appropriately matched to the system, okay, in this manner to get most out of it. So that was kind of the story that I wanted to bring there. The other one, which sort of he asked questions, gave some questions earlier on, which is this constant versus pulse. So capacity can be extended by pulsing the system, by stop using it and restart using it. So what I'm doing is I'm increasing the time to finish, but I'm extending the battery life. Now again, the story is not that easy, because when I'm extending that, unless I truly shut the system down, I will also have some impact because of leakage also. But what's happening from a battery perspective is that by letting it relax, it rejuvenates, and therefore the material inside the battery evens out, and it kind of recovers. It's ready to supply more charge.
Last question?
Yeah.
Is this rejuvenation happens at any time, discharge current, or?
No, so it will be, so rejuvenation will manifest itself when your current was high enough to begin to cause that depletion.
Okay.
See, if you are drawing continual current at a very low level, then the battery will not even see the effect. Okay, so the current have to be larger for this to manifest. So going back maybe like 6-7 years ago, there was a flurry of papers and all where people had tried to explicitly exploit this phenomenon by duty cycling radios, duty cycling processors, stuff like that and all. Some of that work was happening in kind of more contrived battery models. So like they would basically just say, I have a Markov model for the battery or something simple like that, not very realistic model. And the other thing is that on top of the current, the battery chemistries are not always ones, like different battery chemistries exhibit this phenomenon to different extent. So lithium ion doesn't exhibit relaxation related issues that much. Okay, so if you're looking at modern smartphones and all, this is a non-issue. But if you're looking at systems where other battery chemistries are being used, this becomes an issue. So this concept of pulse discharge is basically intuitive, right? I mean, I basically, yeah.
How typically would you see non-lithium ion battery chemistries?
You see it currently in things like drones and cars and those kind of stuff, racing cars and some consumer products where the higher discharge. NiCads do excel in providing a lot of for high power usage, so that's why you still see NiCads in those applications. Okay, and the other thing is also lithium ion, the safety issues surrounding them. So that's the other part. You might recall when the Boeing Dreamliner had come out, its initial battery pack was lithium ion based, and then there were fire episodes or overheating episodes, and then they had to be changed. Okay, so there are some safety issues around that as well. Yeah.
Yeah, so you said higher power. Is that also higher energy, or is it just higher power?
Higher power. Energy, lithium ion is the best we have among rechargeable batteries. Okay. There's something called zinc air, which I have been which perhaps for the last 10 years I have been reading. So a lot of these, I guess what happens is a lot of these things which, like much research, there's a Slashdot article or a New York Times article that this is a technology which will change the world, and then you never hear about it. And so zinc air, I think, fell into that category. Fuel cells is another one which have always been. I still have this 1998 or 1999 Scientific American whose cover was fuel cells. It will revolutionize the battery life of your smartphones. Never happened. So the idea was that you would have, essentially you can just buy these little vials of hydrogen rich fuel and you just swap it, and very long battery life and all. The problem also is FAA never agreed to let it be anywhere inside an aircraft. Okay, I mean, essentially the problem batteries face is that things which help you on energy density side are precisely the one which make them dangerous, and that doesn't work out. So lithium ion currently is, but I think the increasing awareness around safety issues around that it's a pretty serious issue, in the sense that I don't know whether I have already told this story or not, but I have had some pretty serious episodes with lithium ion battery in my lab. One episode, so this is a time when we used to do a lot of underwater work, which again we have started doing. So the problem with underwater work is that when you experiment and all, it's in moist environments and all. So first episode happened, we were doing some experiments in the UCLA swimming pool, and we'll just bring the stuff back. So we brought the stuff back, it's sitting in my lab table, and suddenly explodes. Catches fire. So my student at the time, he was really one of the best electronics focused student I had. So he saw this, he immediately carried the whole thing out into that alleyway between E4 and Volta Hall, and it exploded there. And as luck would have it, UCLA police person was also there, and also he out and all, and so nothing bad happened. But after that episode, we got scared, so because we were working a lot with that, so we bought these sort of bags, which are essentially containment bags. So you put the battery inside it, and then you charge them so that if an explosion does happen, they they control it. They're fireproof, and also it gives you more time. So you bought those. Fast forward another year or so, we began to do experiments in Marina Del Rey. At USC has some space out there, and by that time our hardware had become better, so we were actually deploying it into the ocean water. So this student's apartment was near there, and you can see where the story is going. So we started charging there. Okay, he literally had a lab in his apartment. Okay, total electronics nerd. So what my students were doing were they were basically shuttling back and forth. The batteries were being charged at his home in these bags and all. And guess what? Exploded. But this time around, the bags didn't work. His whole apartment burned down. Okay, so that was fortunately I mean, it could have had much more serious. No one was hurt, and kind of the whole thing just got absorbed as part of the rental insurance and all, because it could have been some pretty complicated. After that, I have, like, my practice is I don't leave anything charging at my home if it is lithium-ion related. It's just too finicky a technology. And I think, again, if you're working with lithium-ion in a lab setting and all, be very careful. It is very susceptible to charging. If you're not charging it properly, all sort of bad things can happen. Okay, and unfortunately, when we work with it, we are using all sort of El Cheapo chargers which we pick up, and all these are not carefully designed stuff in a smartphone. These are some chargers we pick up from SparkFun and all, and kind of working with them. So it's as close to a dangerous technology that you work with in an EE lab, low voltage EE lab, but there's something to just. Okay, so exploiting pulse discharge, I already talked about it. So protocols, operating systems, they all can have a role to play out there. So to vary the speed or duty cycle the stuff. So to summarize then these battery energies, there are basically two main effects. There is an effect relationship between the rate at which we are drawing current and the capacity that we see, and the other one is this relaxation or recovery effect. Relaxation or recovery effect is, like I said, not prominent in lithium chemistry, but is there in other chemistries. Rate capacity effect you always see. So that I guess in some senses is a more universal one. There are additional issues which I have along the way referred to, but there is self-discharge, which is the battery just leaks, okay, and that's intrinsic to the system. That apart, there is another source of leakage which I've already alluded to, that we are unable to shut any system down truly, okay, even in its deepest sleep mode, this will consume some energy. So we have these two sources of two problems which happen when you leave the system for a long time doing nothing. One is that the leakage current in the electronics and all, and the other is the self-leakage within the battery. They both are hurting the lifetime. Cycle life or capacity fading. So what happens here is, every time I discharge the battery, next time around, that CP term is a little bit lower, and it's a little lower. And ultimately, when it hits low enough, usually currently, the number seems to be that when CP lowers by 20%, so like you have lost your peak, your capacity is now 80% of what it used to be, then we declare the battery dead or whatever metrics like that. So I guess target for a manufacturer like Apple is, given their 2-year warranty or whatever, they aim for that your battery life would hit the 80% point no earlier than that period. And then finally, aging, which is kind of related to that, okay? So the difference is the following. Cycle life is that if today I bought the battery and I cycled it 1,000 times, and if cycle life was 1,000 cycles, then the battery capacity would have faded. Aging refers to the fact that I buy a battery and I do nothing with it. It just sits there. I'm not charging, discharging, okay? It just sits there, and it would leak away, and then I decided a year later I'm going to use it, its CP would have degraded. That is because of the degradation in the chemistry of the battery that will happen. So these are different effects, and again, different batteries are susceptible to different things. One of the big improvements that has happened in batteries is that the cycle life has increased tremendously, and that has led to manufacturers being perfectly comfortable just sealing the battery into the unit and then getting other advantages like water resistance and stuff like that. So I guess once the cycle life hit sort of 1,000+ point, that became possible. From what I understand right now, the batteries that you find in the smartphones and all around 1,500 or so complete charge discharge cycles. But complete charge discharge cycles is not what we always do. Many of us do partial charge discharge, and if that's the case, the number goes up. In fact, if you do only micro charge discharge, then it could be hundreds of thousands of micro charge discharge. So the numbers that they're quoting really is kind of near complete discharge and then backing it up. And I would emphasize that term near complete. If you let the battery deplenish completely and not charge it pretty soon, or even let it stay there, then you're destroying the battery as well. So, in fact, to the extent that Tesla, for example, does not consider that if you let your car discharge, then it's not covered under warranty. So, so you're looking at a hit of whatever $15,000 or whatever that pack is.
So on the micro discharge recharge, I believe there was a time where they recommended you always decharge the battery into 20% and then charge it all the way back on.
Yeah,
Is that
so
still true?
yeah. So that's not true, and the only reason for doing that tended to be to calibrate the battery. So for the sensors that, or whatever the, by the sensor I mean software plus hardware, which is giving you the estimate of the battery life and all. The problem is that the only way for it to know this thing is to go through that complete cycle. Okay, but a total deep discharge, like you leave the stuff, damages the battery. Okay. So yeah.
Do you mind adding a little bit information about lead acid batteries?
Oh, it's so stale. Okay, lead acid, right?
But they're still used.
They're used. I think they're primarily. So I guess one reason lead acid is still used is that they are cheap. Another reason they are used, particularly in developing countries and all this, because they're easy to replenish. And just to give you a sense, in my own original home country, India, very common, since electric grid is awful, so very common that we buy so-called inverters, which are basically DC to AC converters together with a big lead acid battery pack. And when the battery kind of begins to die, you put distilled water or whatever into it to kind of just rejuvenate it, okay, and then you kind of extend its life more. So they are easy, and unlike lithium, they are less harsh on the environment in the sense. They still have issues, but lithium has deeper issues, okay. So those are kind of the factors that come into play. So I have to see if there are any other reasons which kind of do it. I mean, the other thing, you're right that I do notice that UPSs that we buy are also lead acid. Still, they are the sealed lead acid types. Sealed lead acid are safe. That's what our cars
Do they
are.
have like an advantage over like power density over lithium ion?
No.
No.
Oh, power density. We can look at the numbers. I have the table.
I didn't see it.
Did I have lead acid there? So watt hour per kg, joules per kg, watt hour per liter. So that's not there. Milliamp, here I don't have lead acid. Yeah, so I don't have that number. But you can see that in terms of at least energy density, it is both volumetrically and mass-wise, it's pretty far behind. Okay, so battery aging, I already kind of mentioned that. but lithium chemistries are affected by aging more so than some of the earlier ones. I think it may also have to do with aging characteristics and also possibly. So the thing to keep in mind is that if you don't use the lithium battery that you have, it's still aging and dying, okay, at a much rate which is much worse than what other battery chemistries have. Okay, so that's an issue with this one. Okay, and yeah, I'll pick up the remaining thread, but there's a lot of newer things, ideas floating around and stuff like that. More efficient stuff, newer lithium-based chemistries, and also, I guess, kind of that magic battery chemistry, which can have a lot of more desirable attributes and be safe and all. Whosoever does it would make tons of money, but remains the future. So next time around, so that would be next Monday, because Wednesday lecture is going to be by my postdoc. We are going to go into these things like how do we manage the battery, how do we model the battery even better than this first order model. So that would take care of, and then we'll go a little bit into other types of energy supplies. So see you next Monday. And again, if you want to meet me, some combination of, you can talk to me after the class today, or Skype, or tweet me next week.